My name is Dániel KODAJ. I'm an assistant professor at the Institute of Philosophy at ELTE, and I'm one of the people who teach in the Master's and the English Master's program. I work mainly on the philosophy of religion, epistemology, and metaphysics. And I'd like to introduce an interesting metaphysical puzzle that was discovered, as far as I know, by a great American philosopher called David Lewis. I call it the problem of quantum immortality. And briefly, the gist of the problem is that, according to a famous interpretation of quantum mechanics, namely the so-called Everett or many worlds interpretation, we should expect to live forever in hell. So we should expect that we will never die, but we will be in more and more pain, we will be more and more miserable, and so on. So in order to see how this problem develops, let's start with Schrödinger's cat. Most of us are familiar with this thought experiment. Imagine that we put a cat in a box, and we also put into a box a device that can kill the cat, for example, some device that can release poison gas. We also put a detector into the box. The detector monitors a radioactive atom that either decays in the next hour or it does not. Suppose it has a 50% chance of decaying. If it decays, then the detector goes off and it triggers the mechanism which kills the cat. So when we put all of this into the box and close the lid and leave it aside for an hour, there's a 50% chance that the atom decays. So there's a 50% chance that when we open the box after an hour has passed, we will find a dead cat, and there's a 50% chance that we will see a live cat. Now the problem is that quantum mechanics describes this situation by attributing a very weird state to the cat. So basically, quantum mechanics says that until we open the box, the cat is in a superposition of two different states, the state of being dead and the state of being alive. And this is represented in the formalism by a state which looks something like this. 50% dead plus 50% alive, or 0.5 times dead plus 0.5 times alive. Now this is not genuine quantum formalism. Quantum mechanics includes complex numbers, not real numbers, as I wrote on the slide. And of course, quantum physics doesn't talk about cats, so the state of being dead and state of being alive doesn't occur in quantum mechanics. There are more exotic states like spin states and positions of particles. But the point of this thought experiment, so this is not a real experiment, but the point of it is to bring out a real feature of quantum mechanics, namely the phenomenon of superposition. And the question is how we make sense of that. So the theory works very well. It works in a probabilistic sense. So physicists can use such states, this kind of formalism, to predict probabilities of events. So if you prepare 100 boxes with 100 cats, then you will find, let's say, 50 of them alive and 50 of them dead after an hour, or maybe, well, of course, these weights can be different. So if depending on what chance the radioactive atom has of decaying. So you can predict probabilities using this formalism, but the question is, what sort of description does this theory give us of reality? So when you close the lid and the superposition develops, what is inside the box? Is it something which is neither dead nor alive, but sort of half this and half that? So one way to make sense of this is to imagine quantum superpositions as being states of some sort of potentiality. So if you imagine that the box contains until you open it, the box contains the potentiality of a live cat as well as the potentiality of a dead cat, and one of those becomes actual when you open the box, then you can take this formalism to describe these states of mere possibility, which become actualized by observation. A more radical and very interesting way of making sense of the situation is the so-called Everett interpretation, which says roughly that the whole question of the transition from the possible to the actual is taken care of in a very simple way. There is no such transition, nor is such a transition necessary for the theory to be in accord with our experience. From the viewpoint of the theory, all elements of a superposition, all branches are actual, none more real than the rest. So when the superposition develops, when we put the cat and the machinery in the box, what happens is that our timeline splits into two timelines. So there's a common history, and then when the superposition develops, what we have in actuality is that reality splits into two. So now there are two different timelines. On one timeline, the cat is dead. On the other one, the cat is alive. This is not an entirely accurate description because it's usually not two branches that develop, but some much larger number of branches. It's very hard to tell how many exactly. But the point is that each branch in the superposition corresponds to an actual timeline in reality. So reality consists of these sprawling alternative histories that branch off from each other, and each of which is perfectly determinate. So it's not like the cat is in a sort of half-dead, half-alive state until we open the box again. It's just that when we close the box, our reality splits into a number of different timelines, and we will continue on one of them. And at each point, at each moment in time on each timeline, reality is perfectly determinate. So the cat is always either dead or alive. It's just that there are other branches where it's in a different state than in our branch. That's interesting. It makes sense of the experimental facts as well as the formalism. The problem, which gives rise to the issue of quantum immortality, is the following. Chemical processes are quantum mechanical. These include biochemical processes, and physiological processes generally work partly by biochemistry. So such death mechanisms as poisoning, infection, and autoimmune disease, ventricular fibrillation, or heart failure are also occasions for life and death branching. Chemical explosions fizzle in very low intensity branches, just as nuclear explosions do. The breaking of macroscopic things, such as your bones, works by the quantum mechanical breaking of chemical bonds. So the problem is that superposition as a real phenomenon is all over nature. For example, it's all over chemistry and atomic physics. Things in our bodies are in a superposition. So this whole problem is not just about experimental situations where scientists create superpositions, but it's really about us as well. So we are in pretty much the same situation as Schrödinger's cat, because each of us are faced with different branches, in some of which we die or we're seriously harmed, and in some of which we survive. So whenever we're in a life-threatening situation, there are branches where we die, but there are branches where we miraculously survive, because it's quantum mechanically possible, it's part of the superposition in question. And so according to the Everett interpretation, there will be parts of reality, there will be real timelines where those miraculous events occur and we keep surviving. Even mechanical processes are quantum mechanical in view of the phenomenon of quantum tunneling. If you stand in front of an oncoming bullet, there are branches of stupendously low intensity, of course, and with negligible chances of being the outcome of a collapse, in which the bullet passes right through you, leaving you unscathed, or less than fatally scathed. If you stand in front of an oncoming train, there are branches of still lower intensity in which you reappear on the other side of the train, or in which not all of you, but enough of you to sustain life reappears. So according to the laws of quantum mechanics, if you leave a system alone, it will develop into a superposition of being at different places, and some of those places will include places where things don't normally go. So for example, according to quantum mechanics, there is a very, very, very low but non-zero probability that if you stand in front of a speeding train, you will not die, but you will just teleport to the other end of the train. That's physically possible, and it's part of the superposition. It's just so unlikely that we never actually observe it. But according to quantum mechanics, it's part of what is there as far as the superposed states are concerned. So if the Everett interpretation is correct, then whenever you stand in front of an oncoming train, which of course you shouldn't do, there will be branches of reality, there will be timelines branching off from the moment when the train reaches your position, where you just teleport to the other side of the train or somewhere else, and you don't die. And this is what gives rise to the problem of quantum immortality. Think of your own future options in the Everett picture. So if you think of what you will experience today I mean tomorrow or a year from now or whatever, in a branching Everett universe, what you should do is first you should disregard those branches where you die, right? Because on those branches you will not be able to enter those branches. You will just cease to exist. But there will almost always be branches which still contain you. So in an Everett universe, you should expect to keep living on as long as it's physically possible, as long as the universe exists and can sustain life. So whenever there's a situation in which on one branch you have a heart attack, on some other branch you miraculously survive the heart attack because of some lucky quantum coincidence, and similarly for accidents and other sources of physical injury. As David Lewis says, according to the intensity rule, you should first discard, when you think about your future possibilities, you should first discard the death branches, if any, and then expect the remaining branches in proportion to their intensities. In the case of the worst dangers we face, the death branches have the most total intensity, the harm branches have the next most, the status quo life branches have much less, and the improvement branches have by far the least. Facing such a branching, you can expect to escape death, but by no means can you expect it to be a lucky escape. As you survive deadly danger over and over again, you should also expect to suffer repeated harms. You should expect to lose your loved ones, your eyes and limbs, your mental powers, and your health. So that's the problem of quantum immortality. If the Everett interpretation is correct, you should almost always expect to survive. Specifically, you should expect to find yourself in the non-death branches that have the most intensity or that are most probable. Those branches will inevitably be ones where you're extremely miserable and get even more miserable as time goes by. So if the Everett interpretation is correct, we are immortal and we are in hell. That's not the only counterintuitive consequence of the Everett interpretation. Think about Russian roulette in the context of the many worlds interpretation of quantum mechanics. So suppose that someone offers you $1 million if you roll a 6 with a die. And if you don't, so if you roll a 6, you get $1 million. In all the other cases, you will be short. Should you accept this bet? Most people will probably say no because, well, $1 million is very nice, but being alive is even better. But if we live in an Everett universe, and if the rolling of the dice is a quantum mechanical process, or if you can convince your crazy millionaire friend to allow you to use some quantum mechanical process to generate the die roll, then you should definitely accept the bet because, well, what are your options according to the Everett picture? There will be branches with a considerably large intensity where you just die, so you shouldn't expect to be there. You're guaranteed not to survive in those branches, let's say, where you don't roll a 6. But there will be branches where you do roll a 6 and you get $1 million. So if you look at all your options in terms of what your experiences can develop into, you should expect to survive the bet and have $1 million. That's because, you know, of all the branchings, the ones where you survive are the ones where you win the bet and you win $1 million. So it seems that another consequence of the Everett interpretation is that you should take every crazy risk that involves potential death versus some benefit. It has devastating consequences to our standard way of looking at things, and the question is what to do now. So should we revise our moral principles and expectations, assuming, of course, that we are Everettians, which many people are? Or should we just hope that the Everett interpretation is incorrect? Or should we somehow refute this argument? This is an example that is quite common in contemporary metaphysics. Contemporary metaphysicians are often interested in the impact of scientific theories on our everyday picture of the world. Often there's a conflict between the way science describes the world and the way we experience the world, or you can uncover some sort of conflict. For example, in this case, it seems that if the Everett interpretation is correct, then we should have very different attitudes to our lives, or at least we should explain why we don't have those attitudes. And philosophers are interested in ironing out these conflicts, in thinking about how we can resolve these conflicts. In this case, one way to resolve it is to assume that we are not identical to our bodies. So if we have minds or souls as well as bodies, and our mind sort of travels along the multiverse, then it's possible that this whole problem will not develop. Thank you very much for your attention.